You guys watch. One just got posted. It is the one that is your homework over the weekend. It's only about 15 minutes long. It's called The Scientific Method, Formulating a Hypothesis. Okay, you learned in like grade school science about the scientific method. You learned about it in whatever science class or biology or whatever you took in, over at your homeschool. That science is about testing hypotheses. Well, what is a hypothesis and how do we do that? How do we come up with a hypothesis? The next video is going to be about testing it, which is way harder than you might think. Okay, and when you learned about scientific method on grade school or something, you had a much simpler idea about it than what we're going to be seeing today, over the weekend rather. So you watch a video. It's only about 15 minutes long, and then there's a little link you go to answer a couple quick questions, and that's where you have it. It's due on Tuesday morning.
Okay.
All right. Last time we made it through the sedimentary rocks and the igneous rocks, and then we took and challenged ourselves by at least starting the metamorphic rocks. And the metamorphic rocks, remember, were the ones that had been exposed to the process of metamorphism, or change. And we said, well, we don't need these exact words right here. Remember, there's a couple of vocabulary words we're going to see in the rest of this presentation. We're going to learn that there are some metamorphic rocks that are foliated. The processes of metamorphism can either be contact metamorphism or regional metamorphism. But these are just the processes that are highlighted by EDSC. Remember, again, these are just sort of our reviewing slides at the beginning. We said pretty much any rock can become metamorphic. In like Magic School Bus, and we watched the Magic School Bus episode again last night, because my kids watch it obsessively. You know, they make it sound like it's a cycle, like you go from igneous to sedimentary to metamorphic and back around. It just goes round and round. Well, it doesn't have to be all the way around the outside. Any kind of rock can become metamorphic. A sedimentary rock could be, an igneous rock could be, another metamorphic rock could get further metamorphism and become still a metamorphic rock. It doesn't have to be. The parent rock, to use the right word, could be any type of rock that can become metamorphic. And we define this idea of metamorphism as being this change that's going to happen in the rock when the rock is exposed to significant increases in temperature and pressure, but not so much that we go all the way back to magma. Going back all the way to magma is not an end of the world too, it's just a different thing. We're just talking about these processes, and in practice this happens a few kilometers below the surface of the Earth. Down deep in the Earth, super hot. Up here, not so hot. There's a temperature difference, there's a temperature gradient, and the farther down you dig, the hotter it gets. Not like right here by the surface, that's more of a weather and climate type thing. But like if you dig a mine, the farther and farther down you go, the hotter it gets. You only have to go down a few kilometers before you're hot enough that these rocks are experiencing metamorphism and have enough pressure on them to be having, well, I'll talk about that pressure in just a little bit. And this is pretty much where we ended the other day, where we were saying, you know, like I said before, metamorphic isn't a yes or no thing. It's how much did it experience. There's low grade, there's high grade, and there's go all the way to igneous activity. And I deliberately kind of put them in this order with these colored arrows on here to make it clear, you know, this is going to probably happen not that far from the Earth's surface. It's just not that hot, not that much pressure. Down deeper, more hotter, more pressure. Down too deep, oops, we cooked our rock. It's lava again. It's magma again. Okay. So let's think about what low-grade metamorphism would mean. It's not going to be a huge change. The rock is different than it was before, but it isn't going to be hugely different. Here's a picture I took from your book. Here's shale. And shale is going to be our parent rock in this case. Shale is a lovely sedimentary rock. Lots and lots of parts of the country have shale. You know, there's soil at the surface and shale beneath it. That doesn't happen to be so much here. Pretty much any place with like natural gas deposits have shale. Shale tends to be what holds the natural gas that we use to like heat our homes and things like that. Shale is a lovely sedimentary rock. But if it somehow, because of the processes of continental drift and mountain building and all that kind of stuff, which we'll learn more about in the next module, it suddenly gets far enough below the surface, so not suddenly, over the course of millions of years, works its way that now this rock is far enough below the surface of the earth that it's hot and it is under pressure. It can metamorphose into, in this case, slate. Shale can become slate. Do you guys know what slate is? Have you ever used anything that's... Slate is what old blackboards were made of. With like chalk on them. Especially the ones that you would hold in your hand. I am old enough that when I was in school, the nuns gave each of the kids a slate of, it was a piece of slate, like a little chalkboard, about the size... I have just totally lost you right here. It was about the size of like a notebook, and like, she'd say, what letter does goose start with? And you write G on there, and you hold up your G. Okay, I'm sure nowadays they do this with iPads or something like that. Right, or Kahoot, was that the name of the app you were telling me to do? Were you doing it on an app? Yeah. Anyway, but we used to do it on pieces of slate. That makes me sound like a group with, I don't know, Little House on the Prairie or something, which is really all that part of the truth.
Yeah,
What?
You had nuns teaching?
Yes. Nuns, yes.
Where'd you go to school?
A Catholic school. anyway, we had slates, old chalkboards, the old ones that were black, and I mean really black. Those, you wrote with chalk on them. Those were slate. When they started phasing them out, they were actually boards that they painted on with chalkboard paint. But they used to always slate. Anyway, slate's a perfectly good rock. It's a whole lot harder than slate is. Than shale is. Shale's actually a pretty brittle rock. You can break it certainly with a hammer, no sweat, and probably with your hands if you've worked at it good. It's not all that strong of a rock. It's not all that dense of a rock. This one's definitely denser. And all those properties of it become kind of clear if you look more closely at it. Like if you kind of zoomed in and looked at it, they're made up of little crystals of minerals. Shale is mostly clay minerals that have been washed out to sea and deposited. And, they went through the process of lithification. But notice how the little crystals are sort of randomly organized any old which way they want. They just fell out of the ocean and landed on the bottom. Maybe they got squished together a little bit, but when they go through metamorphism, the heat and especially the confining pressure, we'll learn about that term in just a little bit, is going to squish them in just as tightly packed as they can be. Now all those crystals are they're just stacked up, they're so nice and so pretty, and now this rock is much denser as in like, the amount it weighs per cubic centimeter or something is greater, and it's stronger. And that tends to be the pattern with metamorphic rocks. They are generally stronger and more dense than their parent was. We could take it even farther and talk about high-grade metamorphism, where it was for a longer time or at a higher temperature or whatever. Here's a nice example of another metamorphic rock. Okay, here is a mineral. This time the parent rock happens to be, I don't even know, I've never heard of that rock before. Granodiorite, I don't know. Mineralogy people are crazy. They have to get any type of rock. I'm looking at that rock, which I've never even heard of before. It certainly doesn't look very sedimentary to me. My guess is this is a granitic type of rock. It looks like it's got a whole bunch of different minerals in it. Mostly feldspar and quartz and mica. Looks like a lovely granitic rock. With lots of felsic and mafic minerals inside of it. That's why it's those different colors. And all those crystals formed as this rock was cooling over millions of years, changing from magma back. And the crystals are just sort of arranged every which way. But heat that rock up pretty darn hot and put it under a lot of pressure, and those crystals start lining up and sorting themselves out. Again, we don't need to know right now as to why that is. But, under the huge amounts of heat and huge amounts of pressure and, frankly, huge amounts of time, the crystals turn and they kind of group themselves together by types, and you get a rock. This happens to be a rock with a weird name of gneiss. That word does not look like it would be gneiss. Or, nice. I'm sorry, it's nice. Nice. Anyway, it's a metamorphic rock, often used in building materials and things like that. Again, it's much stronger and much heavier than the parent rock it came from. With everything just lined up so perfect, it's just packed in there tight. Picture in our house, we've got a big old, like a laundry basket of wooden blocks. Okay? When the wooden blocks are just sort of in there every which way, you can kind of like move them around with your hand. They're not really organized all that. It's not all that strong of a pack. If the kids get OCD and they sit there laying all the blocks in there just exactly right, they stack them in there as efficiently as they can, suddenly it's kind of strong, right? I could stand on that pile of blocks. Putting them in there in order and stacking them up just right, the way these crystals are in here, packed in tight and lined up just right, just makes the whole thing stronger. And also more dense. But yeah, the whole thing, all the bets are off if you heat it up too much. Heat the minerals up of the rock too much and they just melt. That's an exciting thing. Well, it's an exciting thing. It closes the loop of the whole rock cycle, but that tends to happen far below the surface of the earth, and we don't see it, right? This is going to happen, you know, as like rocks are sinking down towards the mantle of the earth or something. All right, so let's talk more about metamorphism. What is this process? How is this actually happening? I'm going to teach you two important vocabulary words here. One is going to be contact metamorphism. And I am angry with the geologist who coined this term, because there's no contact really involved. It isn't like, I don't know, the magic touch. You know, you touch, now you're a metamorphic rock. But what it means is, this rock was close enough to some place where there was magma, and it got hot. So maybe there's some magma, you know, that was trying to rise. Remember, magma rises, it's less dense than the rocks around it. And then it got this far before it was stuck, it was cooling down or something, whatever. But these rocks that are near it are getting pretty hot. They are baking in the heat of that magma. That is contact metamorphism. I mean, you can imagine you can get the rock pretty much as hot as you want the closer you are to this area of magma that is working its way upward. This is a common way to produce, and it's kind of what you think of as being the magma, the process of metamorphism, rather. But another way is going to have to do with pressure. The forces acting on the rock matter too. Now we're going to see in just a little bit, this can be a couple of different things, but the word we're going to be looking for here, as we're describing this, is going to be regional metamorphism. Regional metamorphism is going to be happening where mountains are being built, because I bet you don't need a lot of faith that I'm telling you the truth when I tell you the forces involved in making a mountain are really, really strong. Right? When you're lifting up a mountain range, like what is going on in this picture here. Again, we're going to get into all these processes here where, like, you know, this continental plate is going down and this is being buckled upward. We'll learn all that in Module 2 of the class. But I bet you can picture in your mind, when you think of a range of mountains, that wasn't easy. There was a lot of force involved in making that happen. And those rocks did the work, right? I mean, they were the ones getting squeezed and pushed and forced up and so on. The huge amounts of forces involved, especially during mountain range building, puts huge forces on the rock. I mean, when I hold a piece of rock in my hot little hand here, it looks like a pretty strong thing, and I can't do any damage to it by squeezing, but I'm a wee bit I'm a wee bit weaker than the forces involved in mountain building, right? Expose this to a few odd billion times more power than more force than I can squeeze it, and things start happening inside the rock. Right? There will be changes to the crystals. There will be changes to how they're arranging. This is regional metamorphism. I'm not entirely sure what the sense of the word regional here is, other than like it's because something's happening over its area, like mountains are being built. I don't really like the word contact metamorphism, and I don't really like the word regional metamorphism, but they're not hard to remember. Regional means that it's being exposed to these huge forces as mountains are being built, and contact means it's near heat, like an area of magma or something like that, where it can be exposed to greater temperatures and so on. All right, I'm not going to worry about that right there. Too much verbiage on that one. I meant to pull that one out before I gave it to you. All right, and I apologize. I know some people like to have the slides up as I'm doing them. I know Riley has done that a couple times. I forgot to post the slides. She's sitting there growling at me. Hey, what's this in this picture here?
Statue.
Yeah, do you know where it is? It's Trevi Fountain in, oh, is it Trevi? It's one of the big fountains in Rome. It's this ridiculous what in the world were people thinking when they built such a ridiculous fountain? It's got like angels and demons and horses with wings and Greek gods, and it's got all kinds of confusing ideas in it. And it's all just a ridiculous use of a huge bunch of marble. I tell you this because marble's a metamorphic rock. And I have to have a background for my Bernie slides, and because it drives Mr. King crazy. And he likes PowerPoints, there's so much more marble.
Yes, it's Trevi.
It's Trevi?
I
Yeah, I think it's Trevi. Yeah. Trevi Fountain's a famous fountain. Alright, so what is actually the processes that can make this happen? The book calls these things the agents of metamorphism. What actually can happen? The book gives you four of them, sorry. 4 of them. The actual processes that are happening that make these changes happen. And as you glance at that list, you know how the pattern of this goes. As you glance at this list, you know I'm going to annoy you with each of them separately, because that's how teaching works. And you're already glancing through them and saying, chemically active fluids is something we haven't mentioned before. All right, true that. Let me spend some time, though, on the big ones at the top. It's not a coincidence I put heat there at the top of the list, because heat is our most important agent of metamorphism. Most of the metamorphic rocks that we experience, like marble, are mostly just other rocks that got brought down, by continental drift or mountain building processes down to a depth where there was enough heat that they cooked and they had chemical processes. And how those chemical processes happen is a wee bit of chemistry that you may or may not remember from back when you took it. Just about every chemical reaction out there happens faster the warmer it is. Just about. You probably had lab activities in chemistry lab where you tested that, or the teacher told you that, or whatever, where you're actually learning that chemical reactions and chemical changes happen faster when it's warmer. That's part of why we're warm-blooded creatures, in case you didn't know. Our body's evolution has decided that for us it makes more sense to be warm, so chemical reactions can happen faster, versus us being some iguana who has cold-blooded and has to lay on a warm rock until his body's warm enough for him to actually do anything useful, like, run around and eat spiders or something. Well, there's all kinds of interesting chemical reactions that can happen inside of a rock, too. I'll just pick this pink rock back up over here. And, there's all kinds of minerals right next to each other here. And I bet a chemist could even tell us, hey, that's pyroxene and that's olivine or something. It's neither pyroxene nor olivine, but whatever. Those actually react and produce chemical reactions where they bond, but they also turn at 90 degrees and they line up like this. And that's really interesting. And at what rate would that chemical reaction happen in this rock? It would take it about 1 trillion years to do that. It's a very slow chemical reaction. Well, at these temperatures. Warm this thing up a few thousand degrees, that chemical reaction will merely take 50 million years. You see what I'm saying here? The chemical reactions that make this a metamorphic rock actually happen all the time. It's just they happen so ridiculously slowly at these temperatures and pressures. For all intents and purposes, this thing will never change while it's sitting there on a shelf in my house. Right? On the other hand, bury this under a mountain range, heat it up to 2,000 degrees Fahrenheit, and now we're thinking. Now we're thinking that chemical reaction might happen in a finite period of time. So either bury it deeper, because in general it just gets hotter the deeper you go. You see temperature increases with depth, as we get deeper. Or get it close to some magma that's like working its way upward in a volcano or something like that. Those are good ways to heat the thing up. Even then, the metamorphism won't be fast. It might be tens of millions of years to turn this into, a lovely piece of marble or something. But it will eventually happen, because at least with the temperatures being high, it can happen in like the age of, a few million years. Confining pressure is another agent of metamorphism. Pressure. Now we're going to learn much more about pressure when we do the atmospheric science part of the class. But pressure, when we're talking about confining pressure, this is the part of pressure that is about the weight of the stuff on top of you. Most of what you and I think of as pressure is about the weight of the stuff on top of you. And to make that clear to you, think about going to the swimming pool and going off the diving board. gone off the diving board at the pool and like tried to touch the drain at the bottom of the pool or something like that?
Yeah.
Okay? What happens? It gets harder and harder to get down there, right? The pressure's getting harder and harder on your ears and everything, right? The farther down you go, there's more water on top of you, and all that water has weight, and that is pushing in on you. The word that they use in geology for that is confining pressure. In meteorology, we just call that pressure. But confining pressure is the weight of all the stuff on top of you. So if we are just, this rock is now 2 kilometers down, it's experiencing the weight of 2 kilometers of rock above it, pushing down on it. There's air pressure in this room. There's the weight of all the air on top of us between here and the top of the atmosphere. Well, pressure will cause the rock to experience different chemical reactions or have those reactions happen faster. It's going to generally make the little spaces between the minerals close up as the minerals fit together more tightly. It's going to make the rock more dense. It looks to have a greater density. All that is for confining pressure. And that is different. Oh, sorry, here. I don't care about that. Some of those things are there more just to remind me about something when I was preparing for the lecture. All that is similar but slightly different to what is called differential stress. Differential stress is what we were talking about when we were talking about mountain building or regional metamorphism. Differential stress is when there's big forces acting on the rock and there's more force in one direction than in another. When this rock is under the ground and it's experiencing 2 kilometers of rock's weight pushing down on it, that force is actually pushing in on all sides. Just like right now there's pressure on you from the air around you, the weight of all the air above you. It's actually pushing in on all sides on you. But differential stress is different. It means like there's a giant force acting on one direction. Like as these mountains are being built. So there's a big force one way and a big force the other. That doesn't happen. Meteorologists don't care about differential stress because air doesn't do that. Air is a liquid, a fluid. It goes where the hell I want. So in my experience of things from having a PhD in meteorology, I'm like, I don't give a damn about differential stress. But because I'm not normally thinking about rock. Rock I can push real hard one way and not so hard the other way. I can have less force this way than this way on the rock or something. And during mountain building, this is going to be happening all the time. Huge amounts of force are pushing these rocks upward, whereas maybe there's less force up here as the weight of the rock above it or something. During mountain building, we'll get lots of differential stress. Stress and pressure are closely related ideas. Differential meaning as in it's different in different directions. Again, my background in atmospheric science, we don't care about this because the air doesn't do this, but rock certainly does. And one thing that happens to crystalline materials, like the crystals of mineral inside the rock, is they change when they experience differential stress. And that's how you're going to get this metamorphism happening. As we're building rocks, as we're building mountains, we're going to have huge amounts of differential stress on these rocks. As they experience huge pressures in one direction, and even more huge pressure forces in another. That's different than just the weight of the rock above it. These are the huge forces at work that are building mountains and so on. It also drives chemical reactions that are just too slow otherwise. I mean, I could put this rock in a vise. You know what a vise is, right? It squeezes things. I could put it in a vise and squeeze it pretty darn tight. But even at the amount of forces I could put on this rock, it would take a really long time to make any changes in the rock. Put it under, a million times stronger forces than that, like the kind of forces involved in mountain building, and let it sit there for a few odd million years, we might have all kinds of interesting changes going on inside this rock. As it transformed from being what it is right now, which is mostly sedimentary, into something more interesting. That figure doesn't help me at all. How about chemically active fluids? What the heck are we talking about as that being who's been to Yellowstone? Anybody in this room been to Yellowstone? Oh man, you are missing a field trip. Let's go. Has anyone in this room been to a hot springs?
No.
Dang it, we're going to have another field trip. Yeah, here's the deal. There's plenty of hot water where, like in a geyser, or hot springs or something like that, where water has basically by contact with magma or whatever become very hot, right? And then that's how you get hot springs and geysers and stuff like that. But that hot water usually picks up all kinds of dissolved minerals along the way. That's why, like, if you go to Yellowstone, isn't it pretty when you see those pictures of the geysers and stuff like that? It stinks like high hell there. All those geysers are full of sulfur and all kinds of stinky minerals. They just terrible. Same with like the idea of like a warm hot springs. You know, I've been to a couple of different hot springs over the years. And, you know, they're kind of nice. You go swimming. Oh, it smells terrible there because they're full of the water is actually all full of these chemically active things like sulfur and carbonates and things like that. Hot water gets filled with all these weird volatile chemicals, and these chemicals. So we got hot water, and it's got water with chemically active stuff in it. You know, if that comes into contact with rocks below the surface of the earth that already are hot too, and so on, this might make all kinds of chemical reactions happen that wouldn't have happened otherwise. You know, the water is effectively delivering to the rock chemicals that it wouldn't have been exposed to otherwise, like sulfur in particular. And so you can get all kinds of, I wouldn't worry about, oh, minerals tend to recrystallize and grow longer and all that. That was just kind of based out of the book. I don't care about that. But the chemicals are being delivered to these rocks to change them that wouldn't have gotten there otherwise. They're being transported there by hot water flowing through the rocks and throwing through cracks in the rocks and all that kind of good stuff. So these are agents of metamorphism. So when we actually look at these rocks, how can you tell? How can we tell what's going on? What was this rock exposed to make it the way it was? How do I tell whether it's low grade or high grade or whatever? We're going to go back to a term we used when we did igneous rocks. We're going to talk about the rock's texture. Remember texture? We had exit ticket questions about it and so on. It has to do with the size and configuration of the crystals or grains that made up the rock. I mean, when I grab this slab of basalt off the shelf today, I mean, what I'm noticing here is it's made up of pretty little pieces. I mean, I could probably get in there with like a magnifying glass and see them a little bit better, but it's clearly made of slightly sparkly, but, you know, they're brownish, you know, but they're a little bit sparkly mineral crystals, and so that was its texture. They were very, very small crystals in that case. Here again, we're going to use the word texture to describe these rocks. But instead of describing them as being like large-grained or small-grained, we're going to describe them as being foliated or non-foliated. Oh. Foliated. Who's heard that word before? Or words that have foliated in it? How about exfoliated? What does it mean to exfoliate? Yeah, what is specifically happening when you exfoliate? You're getting more than particles off. You're getting layers of skin off. You're getting like little leaves, little pieces. Isn't that gross to think about? But you're peeling off dead skin. Foliated actually has to do with the word foliage, like leaves. It's like layers. It's like thin little layers like leaves are. Foliated textures of metamorphic rock, it almost looks like a sedimentary rock. It's got layers to it. The layers are not very tightly bound to each other, by the way. Usually with a pickaxe, you can pop them apart. That's what slate is. That's how they make like chalkboards at my little house on the prairie school, apparently, with, right? Somebody mines out a big old piece of slate, and then chips, and they breaks off into these individual chalkboard type, pieces of it. It comes apart in layers. Foliated means like in leaves. An artist will collect their folio of their works. You know, the big book with the big pages. All of the leaves, pages, all comes from folia, foliated. There'll also be the non-foliated sedimentary rocks. So these foliated ones are going to be the ones that have a pretty much flat arrangement of the mineral grains as a result of the metamorphosis going on. Foliated means that they are nearly flat oriented. That's why I don't totally dismiss the idea that this pink rock today might have been at least partially metamorphic. I think it's definitely been exposed to some heat and stuff like that. We get these nearly flat layers in here. I think it's been, they're not exactly flat, but they're nearly flat. I think it's been exposed to some metamorphism. I think there's a couple slides about this actually. Let me just look. Everybody's writing this down so diligently. I hate to interrupt them. You done writing that down, Jacob? Nearly flat arrangement of mineral grains and structural features. All right. So this tends to be, by the way, the ones that were regionally deformed. Good. The PowerPoint's been posted. Don't go nuts. By and large, these tend to be the ones that were going through regional metamorphism. It has to do with the way the differential stresses they produce, the crystals that lined up like that. They've been deformed usually during mountain building. Folding is a type of mountain building. We'll see more of those later. So like, here's a lovely example. We saw this one already, where this was granadine or something like that, and it became gneiss. And so it was just, experienced this metamorphism where there was differential stress, pushing it hard, and it became kind of more lined up, and so you get these sort of bands as what was sort of randomly distributed crystals of different minerals line themselves up and kind of sorted themselves out. You get a rock that looks a little bit more like this. It's kind of got bands of color in it, like that. That's different from the non-foliated rocks. Non-foliated metamorphic rocks, they generally didn't experience much differential stress. They mostly experienced heating. And they got kind of more melty, but they started with crystals kind of oriented any old way, and they still have crystals oriented pretty much any old way. The crystals are basically randomly oriented. So basically think of a rock that's just sort of partially melted. Didn't really go all the way to melt. But it got hot enough that over a few odd billion years, the crystals kind of mush together and so on. Man, it's not too hard to talk about igneous rocks. With a little bit of doing, I can find examples of them. Sedimentary rocks. You go someplace near, you go someplace far, and you see rocks, high probability that they're sedimentary rocks. Remember, 75% of the Earth, of the rocks at the surface of the Earth are sedimentary rocks. You're probably going to see them if you go to a park or something like that. Metamorphic's a little harder. But actually, even in your day-to-day life, you come across some common metamorphic rocks. In fact, your book provides a giant table of them, apparently so that teachers with obsessive compulsive disorder can make you learn the difference between quartzite, gneiss, and schist, and pyrite. I don't want to know about all these different kinds of metamorphic rocks. But I will draw your attention to the two that we've mentioned a couple times. You do not have to know all these guys in, but slate's a good one to know. Slate, it looks like blackboards. It's a rock, don't get me wrong. It isn't like it comes out of the ground as big black sheets. But it's foliated, so you chip at it with an axe or whatever, and it'll fall apart into, maybe a centimeter thick by however big this is, plates. And they can mount them on the wall and use them like chalkboards. Or they can break them into smaller pieces, and nuns can tell you to write the letter G on them. Its parent rock is usually something like shale or mudstone or siltstone. One of these just sort of minerals that accumulated at the bottom of the ocean and it became a sedimentary rock. The other one that's on here that's a real popular, it's really important to know, is marble. Marble, like statues are made of and countertops are sometimes made of and so on. Marble. Donald Trump's toilet or something. I don't know what all is made of marble. But it's fancy, it's nice rock, it is a metamorphic rock. It comes from limestone that has experienced metamorphosis. Remember, limestone was our biochemical sedimentary rock, where tiny little shells of microscopic creatures, maybe even not so microscopic creatures, gradually fell to the bottom of the ocean as they died, and then as they got buried, they went through a process of liquefaction. Marble. This stuff can get exposed to large amounts of heat, and mostly heat in the case of marble, and become a metamorphic rock. That's a good way to know. Do I care about all those other ones? Not so much. though, to know about all these rocks is what are we going to do with them? I picked these rocks up, well, because they were pretty. Actually, I didn't pick all these up. I don't know where I got that one. This one I found someplace on the ground. This one I bought. Well, I didn't buy it. I bought a lot of rocks, and it was at the box with all the rocks. But in general, we do things like, we don't make a thing like, see that mine there? Holy smokes, that's a big, deep mine. Can you imagine how hard it is to drive down to the bottom of that thing? You see what this is, right? These are roads. They go down, they load up the truck, and they come back out. There you can see a truck. Oh, big job. What did you say? That's true.
You gotta look at the bright side of it.
I am looking at the bright side of it. They're getting paid. But that looks horrible.
We don't want to draw.
But there's a whole lot of work there. We only do that, we don't go do that to just get a rock that looks nice. Right? We're doing it because there's something in there that we want, and we are willing to do the work to dig this thing out. There are resources in here that we use. And your book provides you with a diagram here that shows how much stuff we use per person per day, per year rather. So this is how much stuff. Now I know you're thinking, I don't use any sand. No, but like you drove on roads that are made from concrete, so they have sand in them. I mean, you are responsible for some of this. Same with like stones. Well, no, you aren't. You yourself aren't using, whatever. Notice what the units here are, though, just so that we're clear. This is tons. Well, some of this is in kilograms, some of this is tons. I want you to add it up, though. The metallic and the non-metallic things that you use per year adds up to about 12 tons. Some of that is literally like, aluminum and iron and stuff like that, and the things you buy. Some of it is, you're partially responsible for those roads they built, or for that school they built, or whatever. 12 tons a year per person. Meanwhile, other things we pull out of the ground, like energy resources in particular, is another 12 tons. You're responsible every year for about 12 tons of fossil fuels they can put out there. Which, by the way, that's horrifying. Okay, when we learn more about the carbon cycle and stuff like that, you'll learn all about all these, damage that greenhouse gases and stuff that come from you driving your cars to school and all that are causing, that we all do. So right off the bat, just stuff we have to dig out of the ground each year, every single one of you is responsible for about 24 tons of it. The modern world takes a lot of resources. Holy cow. We better start taking a look at this and figure out what these things are for and what we're using them and how we're using them. What are these things? Well, let's go up there and start with the metals. The top one I see up there, the biggest piece, is iron. Dalton, how much iron do you use in a day? Yeah. Macy, what you both recently using iron? What have you built recently using iron in your robotics class or something like that? It's a trick question. You had programs. I know. Okay.
We drink water. That is iron in ours.
Oh,
Bad
like
example.
most forks and spoons and knives, they all have irons, and then some vehicles.
Yeah, what you got?
A hair straightener.
A hair straightener.
Yeah.
Here's the deal. We don't actually use that much iron like in its pure form. Real iron, like a cast iron pan, is actually surprisingly brittle and not all that useful to us. Most iron is used in steel. Steel is way stronger than iron, but the main ingredient in it is iron. Here, there's chairs in this room that are made of steel. Hey, the legs of the tables are made of steel. Hey, about 90% of the weight of your car is steel. Yes.
We didn't know what all these things are.
No, I think we're just talking here about broad. You're not numbering them. I'm giving you a sense here about these materials. Every person in America goes through about 500 pounds of steel a year. I'm sorry, iron a year. That is a lot of iron. Name other things that are made of steel. Roads. Okay? Almost every road is made of, it's got those reinforcing bars, the rebars in there. That's a lot of steel in a road. Almost all construction has steel beams. We go through we gotta mine enormous amounts of iron every year out of the earth. When I'm looking over here at the metallic resources, the next one I see is a person uses 77 pounds of aluminum a year. What do we use aluminum for?
You can put it over your food.
Aluminum foil? Yeah. What else do we use aluminum for? What did you say? I said something. Pop cans? Soda cans?
Can it be used for wiring?
I
think
think
my
there's
house
aluminum
might have
wiring in that.
wiring. It's pretty rare for some reason.
Who's got an iPhone? Who's got, right, a lot of computers or cases are made, or phones are made of aluminum. Cans are made of aluminum, like pop cans and stuff, like beer cans, that kind of stuff. None of that actually adds up to all that much. Almost all of it is used in aircraft. Okay? Aircraft have to be built as light as possible. You see very few iron aircraft. You see very few steel aircraft. The majority of it is used because we need airplanes to be as light as possible. Most aluminum is used in aircraft. It's used in packaging like cans and stuff like that, but the majority is actually used in the aviation industry. But you know what? I mean, we build planes all the time. You're responsible for some of those, right? I mean, some of that weight is on you. Let's see, the next one down there is average American uses about 25 pounds of copper a year. What's copper in? Pennies.
Wire.
Wire.
Common wires.
Copper wire. How about, yeah?
Is it in like telephone wires and stuff?
Yeah, anything like that is going to still be copper.
Isn't there some pans that
Pans have some of it in it. Electric motors have those coils of copper, probably miles of copper wire around, inside there. As the electrical wire, the current goes through there, it produces the rotational force that is the motor. So copper has lots of uses, that's why it's valuable. Mostly, in terms of bulk, most of it is actually in wires and motors, compared to like pennies or something like that. That's a lot of minerals. Hey, the next one is lead. Oh man, my 9-year-old goes apeshit crazy about lead. The schools, they try to teach them to be careful about things like don't eat lead paint or something like that. Good job, okay? But the kids have, and like if they're playing with something that's like an old toy, they tell them to wash their hands because prior to about 1990, a lot of toys had lead in them, in the plastic or in the paint or whatever, and so they're told to wash. My kid, if he knows there's something in there with lead in it, he like runs from the room. What do we use lead in? What is lead actually mostly in?
No, that's graphite.
That's graphite. There's no lead in pencils. That's just a term. Do you know that it used to be though?
Do they have?
Old pencils, like 100 years ago, that actually was not graphite that was in there. Remember we saw graphite that day we did those minerals out there? I showed you. Old pencils, it was lead. But then we realized, it kills people. Yeah.
Then why is it still called lead?
What did you say?
Why is it still called lead?
I don't know, just because the term lead pencil. Yeah, I don't know.
It says it's also used in batteries.
Yes, the main use of lead is batteries. Batteries that they have different lead-based acids in them and stuff like that. Today, most lead is actually used in, but don't get me wrong, there's actually still plenty of awful like paints and plastics and stuff that contain lead. Lead brightens plastic. So like I'm going to go out on a limb here. It is highly probable that this plastic contains at least some lead to get it this way. If it doesn't contain lead, it contains something else horrible like cadmium or something like that that also is toxic. But a small amount of lead added to, this is high density polyethylene that they make these bags out of, makes them bright white. Okay? You've probably seen those bags, I think Kohl's for example, use those bags that are gray. When they don't add any brighteners to the plastic, it turns out that kind of muddy gray color. But it also is easier to recycle and stuff like that. But bright white plastics usually contain lead, but actually not enough lead to make you scared. Hey, well, our next metal down is zinc.
It's used in galvanizing.
Oh, did you know that or did you Google it?
It was on this big sheet of things.
What?
I think that sounds pretty cool.
Is
Just
it
the
what?
word itself.
Pennies? There's zinc in pennies actually, and nickels too, I think.
It's where you wrap something in a protective layer of zinc to keep it safe.
What
Like
is?
iron and steel galvanizing.
Galvanizing. What is galvanizing? She's right. Almost all zinc these days is used in galvanizing. What is galvanizing?
I would say it was exotic.
Oh, it is in sunscreen. Yeah, zinc is in sunscreen. That's true. But by bulk, that isn't that much of it. You're right. No, she's exactly right. Modern sunscreens usually contain zinc.
Especially lubricants.
Is it what?
Or that big summer.
What is galvanizing? She was right. Almost all of it is galvanizing. What is galvanizing? Rust-proofing. Almost anything that you are trying to make rust-proof, you coat it with a thin layer of zinc. That's called galvanizing. It's done electrically, like they dip the piece of steel in they electroplate it. And those things with like thin layers of gold on jewelry and stuff like that. But yeah, zinc. Zinc is one of those ones. It's also what in the firing pins of pistols and a few other things. One of the few things that the Simpsons had right about science is that zinc is used in pistols. But we used a fair amount of it. We had to go find it. Some other things out there too, like manganese. I don't know much about manganese, but manganese is used to produce different kinds of steel and different kinds of aluminum, like for different purposes. I think medical purposes is what we found out last year. And then there's just all these other things. But then we go over to the non-metals, and the big one here is stone. Over 12,000 pounds a year of stone per person. That's a lot of stone.
That's where a lot of the stuff's coming from, that's 6 tons. Right?
Yes, that is a lot. What do we do with all this rock?
Build stuff.
It's a building material. Yeah, I have it up there already. This is building material. I know. I mean, you drive through a neighborhood where they're building it, and you can see a lot. Because does anybody here live in a stone house? Like it's stone stacked up on each other? Is it literally stone, or is it kind of like it's out the outside of the house is stone, and it's not really? Like, is it stone on both sides, the inside and the outside? Cool.
I build
Okay.
my house like that because then it won't burn down.
That's cool. I didn't know. You know, most houses, when you see them, like, you know, you drive down through a neighborhood and there's stone on the outside, it's just a decoration, right? I mean, the real house is made up of 2x4 boards and you know what I'm saying, the structure, and then they put it, same with brick, by the way. There's very few actual brick houses where like the brick is structural, right? It's just a thin layer of brick on the outside, right? Okay, so we don't really use that much stone to like build houses. Where is this stuff going? Horrifyingly, or happily, depending how you think about it, most of this is not like fancy stone, like, you know, marble showers or something like that. Most of this is actually, we get like crushed rock. You know, like the road beds are made up, like if they're building a new highway, they make a big bed of crushed rock, and then the train tracks or the highways built up on top of that, but you know, the road is elevated that way. Well, it takes enormous loads of that stuff to make a road. When I was in grad school, they were building a new highway bypass around Purdue. And I remember it was going to take 250,000 dump trucks of crushed rock to build that road. Holy smokes.
That many just dump trucks entirely full?
Yeah, 250,000 dump trucks of crushed rock is what the article said, to make that road. Crazy. So we go through a lot of it. Let's see, the next biggest piece is sand. What do we use sand for?
Glass.
Glass,
Sandboxes.
sand boxes, sandpaper. We're still not hitting the big one though. What? Yeah, concrete, right? Sand is a big part of concrete. Concrete, you can see the word cement is coming up here, okay? Cement comes from limestone, and cement is the powdery stuff that you mix with water, and then you add the sand to it to get concrete, okay? Well, it's not terribly surprising that we use enormous amounts of concrete. Hold on, I guess it's a little here. Let's go. Where am I at here? Let's go over here. There. Yeah, that by weight, we use an enormous amount of sand as one per person. That's why we have lots and lots of places where we quarry sand out of the ground, like a sand pit. Okay, you go downtown on that trail that goes along the river, and we go down there on the Greenway Passage ever, and you go past the casino, and there's the bend in the trail, and there's that big quarry there, right, where they store rocks, and they,
I know what you're talking
right, they're
about.
mining sand and gravel and stuff right there. Because you're never going to go out of business selling sand to somebody. Okay? We need enormous amounts of sand to be making concrete every day, and sand is heavy. We don't want to move it. It isn't like if there's a great place to get sand in Texas, we're going to bring that sand up to Indiana. It's heavy. It's much better to find sand here, right, in the bottom of the river or something like that. So we get huge amounts of sand for construction purposes, particularly in concrete. They're not quite in order of my slide presentation here. The next one I want to talk about is clay. Everybody in the world is is responsible for about 304 pounds per year of clay. What do we do with all that clay?
I don't know, make potters,
Pottery,
I guess bricks.
maybe bricks, ceramic type things like porcelains and stuff like that. Still not getting to the bad ones. Let's see what all we have in here. Clay's a bad one. Clay, building materials, ceramics, things like that, bricks, stuff like that. But then it starts getting bad. You know what we do with one of the major uses of clay is? It's in.
Did you just say drugs?
That's
what I thought.
No,
drugs.
you're gonna wish it was drugs. It's food. Oh, they add clay to food. Oh no! What are we doing? Are we eating clay? Yes, we are. Wait a minute. I don't mean like guys, if you go to the veggie section, you pick up carrots and celery, you're getting clay. I mean, wash your damn vegetables. No, I mean like you go buy things and look at the ingredients, and it's got clay in it. It won't say clay. It's going to call it a mineral. So that
What is it?
Howlin is one. You'll read the instructions, ingredients of your cake mix, and it'll say that's howlin in it. It sounds like it must be a nutrition thing. No, it's clay. You know what it's there for? Anything that's dried and powdered, like pancake mix or cake mix, will have clays in it because it's an anti-caking. It keeps it from setting up into a big lump. It keeps it powdery.
It says it absorbs oils.
It absorbs the oils, the moisture keeps it from being. By the way, actually, so does makeup. By the way, most makeups have like you guys have seen the people who wear makeup know what I'm talking about. But like the mineral-based makeups, they'll have the same thing. But yeah, it keeps it nice in the package. So when you make cupcakes from your cake mix, it comes out as a nifty, nice powder rather than a big yucky yum. You haven't died yet. Also, it makes you feel full. No, it doesn't taste good, but it makes the add other things to it. But it makes you feel full. It's more satisfying to eat them because it just sort of gets in your stomach and it makes you feel full. It's so gross. Oh man, dog food is largely clay too. Ooh, that's not good. Have you ever wondered how the dog only manages to eat once a day when you feed him? It's because they feel really full after that. Ooh, clay makes me sad. How about salt? I see that's holy smokes, 400 pounds of salt per year. What the heck are we doing with all that salt? You are not eating 400 pounds of salt. Even Latavia, who works at McDonald's, doesn't eat the fries that, you don't eat 400 pounds of salt. Oh my God, that'd be horrible. What do we do with all that salt? That's a little harder one to guess. It's actually mostly used in manufacturing. This is not table salt, okay? By the way, it's also things like for roads, right? Like when they clear sand, they clear snow and ice. Yeah, that's salt too. And we got all these other minerals. Oh man, there's all this horrible stuff in here. Oh, all these phosphates, which are actually used in fertilizer protect, which unfortunately also causes like dead zones in the ocean and stuff like that, and poisonous algae blooms and stuff like that. Oh man, terrible. More of concrete and so on. In fact, there's this huge mineral table there that shows all of them there. Again, I've told you the bad news before. Well, bad or good news, depending on how you think about it. Everything we make, we either grew it or we dug it up out of the ground. It has to be grown or mined. Sometimes a little bit of both. You know what I'm saying? You weren't thinking you were eating things like clay. But you do. Added minerals, it'll say. Ooh, terrible. Hey, I think we reached the end of the material of the lectures for the first test.
No more minerals?
I think we're done with minerals. So here's the deal. On Tuesday, we're doing a lab activity that involves the Play-Doh thing. We're going to be working on building physical models of islands and canyons and stuff like that. And then on Thursday, we might do a lab again, just because I think I want that lab activity on this test, but I'm not sure. Otherwise, we'll start new material by then. And remember, we'll get this all set up, but you take the test out of this room, okay? Yeah, so like during your study hall. How many people in this room have a study hall that they go to? Yeah, there's only a couple people who got study halls that don't have study halls or can't go to their study hall, okay? We'll liven that up with those people, like they'll come and see, yeah, that you got one.
Do we have to do it during a city hall?
No, but that's a great time to do it, but if you wanna set up a different time, like you wanna do it during
Also, does
third period or something like that,
Does it
yes.
set up that, does it set up like a walkout round?
Yes, you know that. Remember we talked about it, most of them will get done.
Like how we used to walk around to kids learning.
Oh, I think,
Or, you know, you just have to.
they were gonna, any career and technical education classes you were in, they were gonna like write off part of the cost of that. Okay, so you probably got like some, maybe you got like a small amount of your money taken back. I'm not sure anything on your schedule counted as CTE. Yeah, yeah. What you got?
Question about the exit.
Okay, hold on just a second. So here's the deal. So probably the plan will be you take okay, I will send you, well, that's a good idea. I have a set of practice questions so that you understand roughly the level of the, you know what I'm saying? I can understand. It can be a little freak out to take your first test with a particular teacher in a particular class. I'm gonna send you a list of maybe 15 practice questions, but you also will have all those materials that help you know what kind of things. The exit tickets are good practice questions too, by the way. And that'll help you, but probably around Thursday of next week, you know, maybe we'll make it Thursday and Friday are the 2 days to get the test done. And you either do it at study hall, or you make arrangements with me to do it some other time or whatever, okay? The test is fairly long. It's usually somewhere around 55, 60 questions, multiple choice, because I gotta keep you busy for an hour. Remember, it's gotta count as an hour.
What if we give them like,
The guidance for the class says that each test should be 50 to 100 questions. We've never hit even as many as 70, so.
I'll about to say.
Yeah, 100 questions is crazy. They're multiple choice, a lot of them are true false, that kind of thing. All right. You do remember to have that video for next time to watch. I'll send out an email to remind you guys, but it's up there for you. Mr. Steele.
I just found the answer to the first minute, it's 100 pounds at kilograms.
Yeah, okay.
That's extremely hard to know
Um,
the answer to.
I said 10.
I will take any answer on there that involves like the amount. What did you find this? All right, I'm gonna stop the camera here.